One, two, three, four, five, six, seven, eight. One, two, three, four, five, six, seven, eight, nine, 10.
This is small demo video to guide participants for their presentations. Hello dear friends and respected teachers, I am going to present and demonstrate the experiment op-amp as an integrator using virtual lab. Let's begin with the introduction of op-amp or operational amplifier. Initially, op-amp was designed to perform the mathematical operations such as addition, subtraction, differentiation, integration, etc. Hence known as operational amplifier. An operational amplifier is a very high gain differential amplifier with very high input impedance and low output impedance. The figure shows circuit symbol for op-amp. It has two inputs. The input can be applied to op-amp through any one of these terminals. If the signal applied to the input terminal results in opposite polarity output, then input terminal is called inverting input, and if output is of same polarity of the input, then input terminal is called non-inverting input. In practice, op-amp device is an 8-pin IC. The second and third terminal are respectively dedicated to inverting and non-inverting inputs. The output of op-amp obtained at 6th pin. The dual power supply is needed for op-amp for its operation. The negative of this power supply should be connected at 4th pin and positive at 7th pin. This is circuit for op-amp as an integrator. Here, input is applied to inverting terminal with respect to ground through resistance R. The capacitor is connected between the output terminal and inverting terminal, and the non-inverting terminal here is grounded. To record the output of integrator with respect to ground, CRO is connected to the output terminal. Since input impedance of op-amp is very high, almost no current will flow through the input terminal to ground. Hence point G can be assumed to be a virtual ground. Hence input voltage can be written as Vi is equal to IR, where I is the current through resistance R. The same current will flow through the feedback capacitor. Therefore, if Q is a instantaneous charge on capacitor, then I can be written as I equal to dQ by dt, as output voltage minus V0 of the op-amp appears across capacitor. Therefore, Q is equal to minus C into V0. Hence, the input voltage can be written as Vi equal to minus CR into dV0 by dt. By rearranging the terms and integrating with respect to t, we get V0 equal to minus 1 by CR integration Vi dt. Now let's discuss the principle of the experiment. Let's take sine input to integrator circuit, that is Vi equal to A sine of 2 pi ft. Output of the integrator circuit will be Vo equal to minus 1 upon Cr integration of Vi dt. So if we use the value of Vi, then the Vo comes out to be minus A upon 2 pi FCR cos of 2 pi ft. So when sine input is given to the integrator, the output will be the cosine signal with amplitude inversely proportional to the frequency of the input signal, the feedback capacitor and input resistor. Let's verify these theoretical predictions experimentally using virtual experiment. This is circuit for op amp as an integrator. The connections are made same as in the theory. Input is given to the inverting terminal with respect to ground through resistance R. C is the feedback capacitor. It is connected between inverting and output terminals. The upper voltmeter to read the input voltage and the lower voltmeter to read the output voltage with respect to ground. The waveforms can be visualized through dual beam CRO. The parameter of the CRO are set to for input wave from -1 to 1, for output wave 0 to 5. The magnified view of the CRO screen can be seen on the right side of the window. Here input resistance I am setting to 500 ohm, the feedback capacitor to 1 microfarad, the amplitude of the input sinusoidal signal I set at 0.5 volt, the frequency I am setting at the 75 Hz. Now let's switch on the circuit. The waveforms will be appeared on the screen, the input waveform at the top and the output waveform at the bottom. Here it is. This is the input waveform and here the output waveform. It can be seen that they are 90° out of phase. Now we can set the another values of frequency. Before that I will record the amplitude of the output. So it will be approximately 2.2. Now I set another value for the frequency, suppose 100 Hz, and switch on. So this will be the output for the frequency 100 Hz. So it is approximately 1.6. So in this way we will set the values for the frequencies at 125, 150, etc. and record the corresponding amplitudes in the observation table. It is seen that the predicted value from the theory for the output of integrator is exactly same as that we get in the experiment. The findings of the experiment: the phase difference between input and output sine waveforms of an integrator circuit is pi/2 radian. The frequencies of input and output sine waveforms of an integrator circuit are same. The amplitude of output wave of an integrator is inversely proportional to the frequency of the input.